So we're jumping into section 12.2 now. We're going to talk about calculus with vector valued functions.
Got it.
Oh. You guys just have to listen to what I say.
Visualize equations.
We're doing interpretive mathematics.
Good ball grass.
That's always the problem with technology, right? It doesn't do what you want it to do. It only does what you tell it to do. So the thing didn't come on and the screen didn't come down when I wanted it to. I had to make it happen. So we're in 12.2. We're going to do calculus with, I'm going to just write VVF, vector value functions. So we're going to start with a lot of what we'll do this semester is take what we know about real valued functions and just extend it to vector valued functions. So we'll say we know this about real valued functions. We'll extend it to these other things that we're working with. So let's think back to when we learned about the derivative. How did we define? I'm just going to say for f of x, how did we define the derivative? Anybody remember how we define the derivative of a function? Equals limit. What is it? Limit is h approaches 0. Beautiful. So there's our definition of our derivative for a real valued function. We're going to define the derivative of a vector valued function exactly the same way. So we're going to say for r of t, some vector valued function, r prime of t is going to be the limit as, and I'm going to use, instead of h, I'll use a little different notation. I'm going to say delta t, just to remind us that we're talking about these small changes. The limit as delta t approaches 0, r of t plus delta t minus r of t divided by delta t. The exact same definition. And we're going to say if r prime exists, we'll call r differentiable. So this is our definition of the derivative. And to put a picture with this, we'll just draw a graph of what we're talking about. So we have here are our axes. And it's really the same ideas we used with real valued functions. So here we have some curve in space, and we're going to draw our vectors here. So this is r of t, and this is our vector after some small amount of time, delta t. And this vector between them, we'll connect those. This is going to be the vector after we subtract, so this is going to be our numerator. This is r of t plus delta t minus r of t. And as we make this delta t, this small change in our parameter, if we take the limit as that approaches 0, we're going to get the derivative r prime of t at time t. So we're just making the time smaller and smaller and smaller. Eventually we get r prime of t at time t. And we can prove this, we can prove using our definition of the derivative that we take the derivative of a vector valued function by taking the derivative component by component. So we just take the derivative of the x, y, and z component. I'm not going to go through the proof, but we just apply this idea, and we would use this 3 times, once for each component. For f, g, and h are functions that define our x, y, and z components of our vector. So I'm not going to go through that. We just use our definition and go component by component. So what we're saying there is, and I'm just going to write out what I just said. So if r of t is f of ti plus g of t j plus h of t k, then r prime is just f prime of t I plus g prime of t j plus h prime of t k. So taking the derivative of a vector valued function is taking the derivative of the component functions. Now we have, because we're dealing with vectors, the properties of the derivative have some interesting differences from our properties of derivatives with real valued functions, because we're dealing with vectors. And then we can also we can talk about dot products and cross products. So with real valued functions we have the product rule. With vectors we have different kinds of products. So we have couple of different product rules, and then we have some other interesting things that come out of taking the derivative of a vector valued function. So we're going to go through a list of the properties of the derivatives of vector valued function, and these are going to become much more important when we start talking about vectors on surfaces. We'll use these properties quite a bit. So our properties. The first ones are really easy. We're just dealing with scalar multiplication and that kind of thing. And then we get into the more interesting ones. So for all of these, C is a scalar. F is a differentiable real valued function. And R and U are differentiable vector valued functions. So we're assuming that all of our functions here are differentiable, and I'm going to say C is a scalar. We can say C is a scalar. So yeah, we're good here. All right. So our first property, ddt of a scalar multiple is just the scalar multiple times the derivative. So that one's nice and easy. The derivative of a sum is the sum of the derivatives. Another easy one. And I'm going to drop the t's here just to make it easier to write. So this is going to be r prime plus u prime. We have three product rules. The derivative of f of t times r of t is f r prime plus f prime r. So just that one's just our familiar product rule. F is a real valued function. The derivative of a dot product is r dot u prime plus r prime dot u. The derivative of a cross product. We have different ways we can take products of vector valued functions. So r cross u r cross u prime plus r prime cross u. And remember, our cross product is not commutative. So order matters when we do the product rule with the cross product. The dot product is commutative, so we can do these in either order, but the cross product is not commutative. A couple more properties. These are the ones that we use to prove things a little later in the semester. Let's see. We have a couple of chain rule. We'll have the chain rule. So our chain rule is the derivative of r of f of t is r prime of f of t times f prime of t. So this is just our familiar chain rule, but we have our vector value function. Two more properties. If r dot r is a constant, then r dot r prime equals 0. This is an important one. This one comes up later when we start talking about derivatives of vector value functions in terms of velocity and acceleration. So thinking back to just to basic ideas of vectors, what quantity is r is the dot product of a vector with itself? Do you remember what quantity that represents? Nobody remembers? That's a square of the magnitude. So if the dot product of a vector with itself, so that's a square of the magnitude. So the square of the magnitude is constant here. And our last property, finally, if r prime of t equals 0, then our curve represented by r of t has a cusp at that particular value of t. And kind of a corollary of this property is that r prime is smooth everywhere that r is smooth everywhere r prime does not equal 0. So those are our properties of the derivatives of vector valued functions. The main ones that we'll be using today for the next couple of days are our product rules and our chain rules. Just basically practicing taking derivatives of vector valued functions. The important one to remember is the derivative of a cross product is the order matters if we use a product rule. Now, when we use a product rule, we could always just do the cross product first and then take the derivative. It just depends on how much work one or the other is going to be. So if we use the product rule here, we have to do the cross product twice. We can't always just take the cross product and then take the derivative. So it depends on how you want to go about the problem. Some of the problems in the homework will ask you specifically to carry out use the product rule. Just to kind of practice and remember what the product rule tells you. Questions on our properties. I just want to do an example of calculating the derivative of a particular vector valued function. So we're going to calculate a couple of quantities, a couple of derivatives with a vector valued function, and that's really all I wanted to talk about today. All right, so let's look at an example. So we have r of t. Our vector valued function is cosine pi t I plus sine pi t j plus t squared k. And we're going to say that t0 some particular time is negative 1/4. We want to find, for this particular function, we want to find r prime of t0 over the magnitude of r prime of t0. And we're going to find another quantity. We're going to do two derivatives, r double prime of t0 over the magnitude of r double prime at t0. So if we were thinking of r as a position vector and how would we interpret r prime and r double prime? Velocity and acceleration. So if we're finding r prime over the magnitude of r prime, what are we looking at? Unit vector in the direction of the velocity, right? So we're looking at unit vectors here. We're calculating some unit vectors in the direction of our velocity, in the direction of our acceleration. If we're interpreting this as a position vector and t as time. So before we start taking derivatives, what kind of motion is this describing? So Sean says an accelerated spring motion. So because it's as t increases, the z, we have a quadratic relationship in the z component. So it's going to be like a stretched spring that's getting more and more stretched as we go up the z-axis. All right, so let's calculate our derivatives, r prime. So what's going to be our derivative of r? Negative pi sine pi t I plus pi cosine pi t j plus 2tk. At t0, r prime of negative 1/4, I'm just going to plug in negative 1/4. I get pi square root 2 over 2 I plus pi square root 2 over 2 j minus 1/2 k. So I'm just plugging negative 1/4 in and calculating. The magnitude of r prime at t0 is going to be the square root of each component, sum of each component squared. When I calculate that out, so x squared plus y squared plus z squared basically, when I calculate that out, I get 1/2 the square root of 4 pi squared plus 1. So I calculate that, do a little simplification, and I get 1/2 square root of 4 pi squared plus 1. So then we can find r prime over the magnitude of r prime when we, so this first quantity that we're looking for, is just going to be 1 over square root of 4 pi squared plus 1. I have these 2's in the denominator, and I have this 1/2. So the 2's are going to calculate or cancel all these 1/2's in my original vector. So I get times pi square root 2 I plus pi square root 2 j minus k. And that's that first quantity that we're looking for. And actually, I think that's enough. We could go through and calculate this second quantity. Same process. We would take the derivative of this quantity, substitute our t0, find our magnitude, divide the vector by the magnitude. So we're just doing the same thing over and over again. So I'm just going to write down here, repeat process for the second quantity. But taking derivatives of vector value functions should be very familiar. Whenever I work with the derivatives like this, I think it's just like using real value functions, except you have to do everything 3 times for x, y, and z. So any questions? Any questions on derivatives of vector value functions? No questions? just a nice little, again, we're just kind of slowly dipping our toes into working with vector value functions.